Okay, this is lesson 7. This is the last official lesson for atomic theory, and I will do one overall review video after this. So today we're going to talk about the difference between ground state and excited state electron configurations and what's happening in terms of energy when that happens. So let's look at the difference between ground state versus excited state. First of all, when we look at neon on the periodic table, we can see that its electron configuration is 2,8. Now, remember, we haven't talked about bonding yet, but atoms will tend to lose or gain electrons so that they can achieve a stable configuration, meaning 8 in their valence shell. So, for example, sodium has an electron configuration of 281. It will want to give up 1 electron in order to have 8 in its valence shell. Fluorine, on the other hand, has an electron configuration of 27. It wants to gain 1 so that it can form 2,8. So everyone, when they combine to form compounds, when they bond, they all want to achieve 8 in that valence shell to be happy, stable, content. Now what happens when we go to the excited state, an electron will jump from a lower energy level to a higher energy level. So here, one of the electrons in the second principal energy level jumped to the third principal energy level, right here. So now the electron configuration is 271. So the excited state is when an electron jumps to a higher level, leaving a lower level partially filled. Remember, we talked about that there are 4 principal energy levels, PELs, and they're numbered 1, 2, 3, 4, 5, 6, 7, so on, because each period represents, each horizontal group represents a principal energy level being added. Now the first principal energy level can only hold max electrons of 2, the second can hold a max 8, the third 18, and the fourth 32. So these numbers represent the max electrons in each principal energy level. So what happens when something's excited, it jumps from a lower level to a higher level, leaving this partially filled. So the second principal energy level can technically hold 8. Another thing is that the ground state is what's found on the periodic table. PT for periodic table. And the excited state is not found on the PT, periodic table. Okay, so let's give a formal definition here. Ground state, electrons in the lowest energy level possible. So that's a configuration found on the periodic table. Electrons are closest to the nucleus as physically possible, meaning as close as the max number of electrons in each principal energy level will allow. So meaning 2 in the first principal energy level, 8 in the second, so on and so forth. The ground state electron configuration for Li is 2-1, and this is what we find on the periodic table. Excited state, electrons are found in a higher energy level, and this is not found on the E configuration, is not found on the periodic table. So therefore, an excited electron configuration for Li could be the reverse of this. It could be 1, 2. okay, because normally there has to be 2 in the first principal energy level, or 1, 1, 1 is also another example of an excited state. Let's do some practice ones. So 2, 1 we know is already, we just did this one. This is lithium. So we know that this is found on the periodic table, so this is ground. 2, 0, 1 is not found anywhere on the periodic table. Technically, there should be 8 in this principal energy level, so this would be excited. 1, 1, 1, we gave this as an example of the excited state for lithium. 2, 7, 3. Our rules tell us that in order for this to be ground, there would be 8 where this 7 is. So this is the problem. I'm going to circle the problems. So this is not filled, this is not filled, and this is not filled. So this is also excited. 282, we can find that on the periodic table. That's magnesium, so this is going to be ground. 2882, we can find that on the periodic table, so this is going to be ground. 28176, remember, the first can hold 2, the second can hold 8, the third can hold 18. So that's excited. One of these electrons jumped from the third principal energy level to the fourth principal energy level. 28188, that's found on the periodic table, so that's ground. 26, well, there's the problem right there, because that should have 8 before we add any more. Therefore, this is excited. And the same is the same problem with this one. 2, 5, that should have 8 before we continue. So that's also excited. So remember, if you can't find it on the periodic table, it's excited. Now, how can you take something in the ground state and make it excited? So let's just take calcium here, for example. So this is ground state. Let's say I wanted to make that excited. How could I do that? Well, I could take any one of these and move it up. So let's take one from the second principal energy level, make that a 7, and then tack it on to the last one. That's an example of excited. I could have moved one of the first ones. I could have made it 1, 8, 8, 3. Okay, so there's more than one possible correct answer for excited. You're taking one from a lower state and jumping it up to a higher state. One thing that's very important between the ground and the excited state is that the number of electrons must remain the same. So for example, here I've got 20 electrons. In this example, I've got 20 electrons. So both have 20 electrons. You're not gaining or losing electrons here. You're just moving where they are. Okay, so let's talk about energy now. This is really important, and you need to know this. They will test you on this. The greater the distance from the nucleus, the greater the energy of the electron. So if I have, so what that means is an electron in the third principal energy level has more energy than an electron in the first principal energy level. And you'll understand why in a minute. Because when you go from the ground state to the excited state, when that electron jumps from a lower level to a higher level, energy is absorbed. This is very important. So an electron in the third principal energy level had to absorb energy to get there. So it's going to have more energy than an electron in the first principal energy level. When we go from ground to excited state, energy is released in the form of light energy. Think about it this way. When you go upstairs, you need energy to do it. Okay? You need energy to do it. When an electron goes from a low level, so here is sodium. It has an electron configuration of 281. So when this electron jumps from here to here, it's going basically up. Therefore, it needs, so this is going to be ground. If I do it down here, excited, 273. So now, when it went from here to here, it had to absorb energy to do it. So when you go upstairs, you need energy. That's one way to help you remember it. These are showing you some examples. A solution containing lithium gives off red light. I wouldn't say that it's really red to me, and you'll see this, it's more magenta than it is red. A solution containing sodium will give off yellow. A solution containing potassium gives off a blue light. Well, I beg to differ here because potassium tends to be a bluish purple. You're definitely going to see some purple in here. And we're not going to work with rubidium, but rubidium gives off a lavender light. So when we heat a solution that contains metal ions, the electrons become excited and they jump from lower energy levels to higher energy levels. And this happens like instantaneously. When they drop back down to a lower energy level, when they release that energy, it's in the form of light energy. And that's what we call spectra. It's what we can see. And each particular element has its own spectra. So when atoms absorb energy, their electrons will shift to a higher energy level, or what we call the excited state. This is a very unstable or temporary state. So the electrons will fall back down to a lower, I reverse these two words, it should be lower energy state level, or ground state. When they fall back down from the excited state to the ground state, they release energy in the form of light, which is called spectra. Different elements produce different colors of light or spectra. These spectra are unique for each element, just like a human fingerprint is unique to each person. We therefore use spectral lines to determine which element we have, because each element gives off a characteristic bright line spectra. And this is used, you know that stars are made of gas, right? So scientists can analyze the gas in the stars to determine which elements are present. So this is kind of like when the police run a fingerprint through the DNA database to determine if there's a match with a suspect, if we have their DNA sample on if we have their DNA sample on file. It's unique to each person, so it matches that print to that person. Well, it's the same thing when we analyze the gases in the stars. Each element has its own spectra, so we can determine which elements are present. Here's an example of how it might be presented on an exam. So you have this unknown mixture, and these are called spectral lines. And we can compare this to known samples. So in order for a gas sample, so these are the spectral lines for gas A, gas B, C, and D. In order for the gas to be present in the unknown, all of its spectral lines must match up. So you can see that gas A is definitely present because all of its spectral lines match up. Gas B is not present because these lines are not here. Gas C is not present, but gas D is present. So we know that gas A and gas D are in the unknown mixture. Okay, that's it for our last lesson. Have a great day and keep an eye out for the review video.